Hello friends. So today we are going to solve 4 questions, and these 4 questions will be from our electric potential. Okay, 1 second. So in first question, it states that a spherical shell with its R and surface charge density sigma is sandwiched between two infinite sheets with surface charge density minus and plus sigma as shown in the figure. If the potential far to the right, that is at x equal to plus infinity, is taken to be 0, what is the potential at the center of the sphere and at x equal to minus infinity? So basic figure is given to us. So we have two sheets, one to the, suppose this is the center of the sphere, and we take this center as x is equal to 0. So left side will be equal to over minus r and right side will be over plus r. And we have a sphere that is sandwiched between the two. And in this case we are given that we are having a, you can say, potential at x is equal to plus infinity is said to be taken as 0. Okay, whereas we have to find out what will be potential at x is equal to minus infinity, that we have to find out. So we are given, and so let us state that the center of sphere we have taken as at 0. We can say that center of sphere is suppose given as our O. Therefore, the center of sphere, we have taken this as origin, that is our x equal to 0. Okay, so it is entirely lying on the x-axis. So this is our x-axis, and obviously this is our y-axis. And so this will be our left sheet and this will be our right sheet. Okay. Therefore we can say that our left sheet will be at x equal to minus r, and our right sheet will be at x equal to plus r. Okay, so this is given to us, and it is also given that potential at plus infinity is equal to 0. This is also given to us, and we are supposed to find out what will be the potential at the center, that is at O. We have to find out this one, and we are also going to find out what will be the potential at minus infinity. So we have to find out these two things. Now if you look closely, at least for one thing we are very sure, that the potential at the center will be the effect of the sphere's potential, and the potential because of our left sheet, and the potential because of our right sheet. Okay, so all the three is going to influence the potential at the center. Then later on we can just discuss how the potential at the minus infinity can be found out. Okay. So we are going to treat these, you can say, in two different two separate objects. First we are going to discuss sphere independently, then we are going to discuss the left sheet and right sheet independently, and then we are going to, you can say, solve it with respect to the potential at the center. So let us start with our sphere, and for that we can see that electric field of the spherical shell, okay, this is not sphere, sorry, it is a shell. It is a shell, not a sphere. So here it is given as a shell. And so we start with our electric field of the spherical shell. So field of the spherical shell, and in order to find out, first of all we are going to find out the total charge on the shell. So we have total charge on the shell, and let us suppose our Q. So Q will be equal to over 4 pi r square times the charge density. Okay. And then in order to find out electric field, we can find out, use the Gauss law. Okay. So you can say from Gauss law, and for Gauss law, if we had taken a Gaussian surface of radius small r, which is less than our radius of our shell. Okay. So under this condition, we know that the charge enclosed, that is our Q enclosed, for this condition will be equal to 0. Therefore, we can say that the electric field of our shell for the first condition is equal to 0. Then we come to a second condition, that our Gaussian radius, that is our r, is greater than the radius of our shell. So obviously the charge enclosed will be the total charge Q. Okay, so we can say our charge enclosed will be equal to total charge Q. So based on this, we can write that electric field of our shell at a distance r will be equal to 1 upon 4 pi epsilon naught, and this comes as Q upon r square. And based on this, we can also find out, because we know the electric field, now we can easily find out the potential of the spherical shell. So you can say potential of the spherical shell, and we know that the potential inside the shell is constant and is equal to our surface value. So it means when our inside point, we know that our potential of the shell for the condition when the radius is less than our radius of the shell, this will be equal to over 1 upon 4 pi epsilon naught Q upon r. And in terms of charge density, we can write this as sigma r upon epsilon naught. Okay. So from here, we can clearly see that this relationship is independent of small r. So this is an important conclusion here, that this result is independent of position inside the shell. It means if this is the shell and this is center, then this r point can be somewhere here, 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 and here. Okay. So this potential will be always equal to same, or we can say it will be constant. Therefore we can say this result is independent of position inside the shell. Position inside the shell. Now we come to our sheets. So we are going to find out now electric field of the two infinite sheets. Field of two infinite sheets. And so we have to remember that the general formula for the field because of a single infinite sheet, so we can say that our field due to single infinite sheet, and that is suppose our E, then this E will be equal to charge density upon 2 epsilon naught. So the field due to the sheet is also independent of the distance. Okay, no matter if this is sheet, no matter where we take this distance r, so this can be also r and this can be also r. The value of electric field will be our same. It is independent of our distance of the point where we are going to find out the electric field. So this is the important part with respect to our this sheet. Okay. And we also know that if depending upon our charge density, okay, so if charge density is our greater than 0, which is our basically positive, then our electric field is directed away from the sheet. Directed away. And if we have our charge density is less than 0, which is our negative, then it is directed toward the sheet. Toward the sheet. And here away from the sheet. And in case of the two parallel sheets, we are just going to use the superposition principle. Okay. And for that, we are going to define, we already done this question many times. So we have two sheets, okay, and this is our minus sigma and plus sigma. So let us suppose this is our region number 1, region number 2, as well as our region number 3. Okay. And okay, let me define it other ways. So this is our region number 1, 2 and 3. Okay. And we know that this is the center and our right side is at our plus of r and left side is at minus of r with respect to our sphere. Therefore, we can write for region 1, because this entire is lying on our x coordinate. Okay, so this is our x axis and this is our y axis. So for region 1, we are having that value of our x coordinate is greater than our plus r. And so we can easily find out what will be the value of our net electric field in the region 1. Okay. So region 1 is, suppose this is the point. Okay. Let us call this as our point P1. Here we are going to find point P2 and this is a point P3. So we have point P1 randomly at any place, distance doesn't matter here, and we know that our charge density is equal to positive, electric field is directly away from the sheet. Okay. So because of this, the electric field, because of our positive, will be directed away. So this will be electric field due to our positive, and electric field due to negative will be directed toward the sheet. So this will be electric field due to negative. And once again, one second. I think there is some 1, 2, and 3. I think this is okay. Looks good. Okay, so let us. Therefore, we can write therefore we can say that our net electric field, because of our at x is equal to plus r, will be E of x, and that will be coming equal to our minus sigma upon epsilon naught. Okay, and region 2. Okay, so one second, I think my mistake, sorry. So this is our point 1 and directed away from the sheet. Okay. So this is directed away from the sheet. So this is first sheet, and this is our plus r, and then we have our second sheet, that is minus r. Okay. And in this case it will be directed toward the sheet. Okay. Yeah. So we can say that the value of electric field is equal to minus sigma upon epsilon naught. Now we come to our region 2, that is point P2, and point P2 is somewhere here. So our electric field will be directed toward, and it will be toward the sheet and away from the sheet. So therefore we get, when x is our greater than minus r but less than plus r, so we are talking about point P2, and in this case we get that the value of electric field will be having the 0. Okay. And finally we are having in the region, third region, and third region is our somewhere here. So this is our P3, and in this case we are going to get, it is in this direction. Okay. And therefore we get that the value of electric field will be equal to our plus sigma upon epsilon naught. So we got the value of electric field for all the three regions. Okay, and in this case we have to make sure that so we can just draw a conclusion from here that our plate field is 0 where the sphere is, sorry, not sphere but shell is. Okay. So which basically means that these were our two plates and in between there was a shell. So the field, because of the plates in between, is our E of x, which comes equal to 0. Okay. So it means if we want to find out the effect of our electric field, then only the electric field because of the plates will be only in our region number 3 and region number 1. In region number 2, the plate field is equal to 0. Okay. And the sphere is also present in our, sorry, not sphere, but shell is also present in our region number 2. Okay. And second thing from here we can say that our plate field is non-zero outside. Okay. Outside means our region number 1 and region number 3, and inside means region number 2. Okay. So here we draw this important conclusion. Now let's find out what will be the potential due to the plates. Potential due to the plates. And in the question it is given that our potential at plus infinity is equal to 0. This is given to us. And once again we are going to solve this potential with respect to the regions that are known to us. Okay. So we start with our region 1, and region 1 is our x is greater than our r. And the value of electric field in this region we have already found out, that is minus of sigma divided by epsilon naught. Therefore, we can write that potential at x is equal to plus r, and let us suppose that is equal to v is equal to plus r, and which will equal to minus of our electric field in that region and derivative of our x, and the limit will be from plus infinity to our plus r. Now we substitute value of electric field. So we get our potential at plus r will be equal to, this comes as plus infinity plus r minus sigma upon epsilon naught times dx. Therefore, we get at potential at plus r will be equal to minus will be our plus epsilon naught and times r. So this is the potential at distance r. Okay, and this r it can be at any position but on the right side of our disk plate. So this point can be anywhere in the right side of the plate. Okay, because this is our plus r and this is our minus r. Okay. Now we come to our region number 2, and region number 2 is between our minus and plus r plus x. So this is x greater than minus r and less than plus x. Okay, so the region number 2 is lying between the two plates, and we know that the electric field between the two plates is equal to 0. Okay. Therefore we can say that our potential because of our plates at center will be equal to potential at a distance r. Okay. And this is sigma r upon epsilon naught. Okay. That is our same. And we are simply going to, you can say, because we know that the shell is also contributing the potential at the center. Okay. So we can say that our potential due to shell at the center, okay, which we have calculated at the start. Okay. So we can say V shell at the center is equal to our charge density divided by epsilon naught, which we have already calculated. Yeah. Sorry, not this one. Okay. And now we are simply going to, you can say, add them. Okay. But we have to remember that we calculated this potential of the shell is defined with relative to the infinity, and that is without the plates. Okay. So we can say from here that this shell potential is defined relative to infinity. Relative to infinity without plates. Okay. Like I said, we divided this entire problem into two parts. First, we considered a shell independently. Okay. Then we considered our two plates independently. We calculated our potential because of the shell at the center, which is our first step, and then we calculated the potential because of the plates at the center, okay, which is our this one. Now we are simply going to solve this. Okay. And we also know that in case of our potential at our, so you can say that potential at the center, that is our V of 0, will be equal to potential because of our plates at the center minus 1/2 potential because of our shell. And we have calculated both the terms independently. And in case of our plates, that is our sigma r upon epsilon naught. So this comes as our sigma r upon epsilon naught minus 1/2, and we have also calculated, that is our sigma r upon epsilon naught. This comes as sigma r upon epsilon naught. Therefore we get that our potential at the center, that when here 0 means at x is equal to 0. Okay. So in the starting we have already defined it, that this point is our x is equal to 0, okay, which we are going to find out. So we get this as our sigma r upon epsilon naught. So this is the potential at the center. Okay. And so this was our first part. And second part, we are also going to find out what will be the potential at x is equal to minus infinity. We have to keep in mind that potential at plus infinity is given to us 0, which means that potential at when x is equal to plus infinity is given to us as 0. Okay. And we have to find out what will be the potential when x is equal to minus infinity. So we can say our potential at x is equal to minus infinity, or we can say we are going to find out v of minus infinity. This we are going to find out. And we already know that between the plates, that is for plus r to minus r, okay, there is, we can say, no plate field. No plate field. Plus r to minus r is nothing but our region number 2. And region number 2, we found out that the value of electric field is equal to 0. And now we are interested in from minus r to infinity. That is our minus infinity. Okay, so we are interested in this. And we already know that this is our region number 3. And this region number 3, we know that the value of electric field which we calculated is our plus sigma upon epsilon naught. Therefore, we can write that potential at minus infinity will be equal to potential because of our plus r plus integration, and that comes because of our this sheet, that is our sigma epsilon naught times dx, and it comes from minus r to minus infinity. Okay. And so it is quite simple to calculate, not much of things required now. And this v of r we already know is our sigma r upon epsilon naught, and this will be coming a plus, and it will be sigma r upon epsilon naught. Therefore, we can say that our at minus infinity, we are going to get this as our 2 sigma r upon epsilon naught. So this is the value of our electric field at minus infinity, sorry, potential at minus infinity. Okay. So I think these were the only 2 things we have to find out, but we have to keep in mind that the basic figure that was given to us was something like this. Okay. So in the first part, we have to find out what will be the potential at the center, and the potential at the center will be the potential due to this shell and potential due to the 2 plates. So we divided this entire discussion or solution into 2 parts. In the first part, we considered the shell and found out the potential at the center. Then we considered independently 2 plates and found out what will be the potential at the same point, and then we added them. Okay. And same thing we did for the potential also, because we know that our electric field of our sorry, not electric field, but our potential, that is v of r positive. So we already know this, and because of these 2 sheets, we also know that our potential will be only because of on the right side. In between, there is no potential because of our electric field. Okay. So yeah, so this was a final part. At x equal to minus infinity, we found out that that was a region number 2. The electric field was equal to 0, and this was our minus r, and this was our plus r. And in region 3, so this was our region 1, this was our region 2, and this was our region 3. So this was a different approach, or we can say a little bit different numerical to sort it out. Next question, we are given that the right angle triangle as shown in the figure with vertex P at the origin has a base B, altitude A, and uniform density of surface charge as our sigma. Determine the potential at the vertex P. Okay, so basic figure, let me draw it here. So we are given a coordinate system, and we are having a right angle triangle whose vertex is at P. Okay, and this right of triangle is something like this, and this base is given as B, and the altitude is having our A, and let us suppose this angle is our theta. So this figure is given to us except the angle theta. Okay. And so like P was, it said that it is at the origin, so this coordinate will be our 0, 0. Okay. And let's call this as our Q. This Q will be equal to our B comma 0, and let us call this our R, and this R will be equal to our A comma B comma A. And so let me, this coordinate will be our 0 comma A. So we just defined the coordinates here. So we can say that our tangent of theta will be equal to our A upon B. This is nothing but our right angle triangle. And we know a general expression for our potential. For that, we can say that general expression for the potential and the potential at point P, that will be equal to 1 upon 4 pi epsilon naught, and our charge density dA divided by R. Okay. And let me draw this triangle separately. So this is our point P. We considered a small area, that is our dA, at a distance r from this point. So with respect to this, we can write this formula. And next we can find out what will be the potential contribution because of this strip, that is our dA. So for that, let us write that consider a vertical strip of area dA at distance r from point P. Therefore, from here we can write that the potential from the strip potential from the strip. This potential, let us call this a d of phi. Then we can write this as d of phi. One second, I missed something. Yeah, sorry, we will come to this because we have to define the coordinate first. Okay, then we can just easily find out. So we consider this strip, and so we can say, because we need to integrate it, and for that we need to find out what will be the limits in y direction. Okay, then only the integration will be possible. And so we consider this strip of area dA, okay, and width dx. Therefore we can say that our, and for the sake of simplicity, let us call this our point x at a distance x, and width is of x. Okay, so this will be x now, okay, because so let's find out the limits in y direction. Limits in y direction, and for that we can simply write the equation of the hypotenuse. So we can say equation of our hypotenuse, and this was our p, q and r. So we are interested in equation of a hypotenuse, that is our pr. Then this pr will be equal to y, and we know that this our entire is given to us as a b, and the altitude is given as our a. So the equation will be equal to over a times 1 minus x upon b, because p is at the origin. And for a given value of x, the y is going to vary from 0, 0 up to this value. So we can say that for given x, our y will be greater than 0 but less than equal to a1 minus x upon b, and our x will be varying between our b and our 0. So we found out the limits in which our both the variables as x and y is going to vary. And this is somewhat you must have studied in mathematics. That is, I think, something, the topic is something about area. I forgot the name of the title. Area under the curve. Okay, so in area under the curve, okay, we deal with this kind of limits, okay, because we have to find out the area under the curve. Therefore, so we got the limits within which our y and x are going to vary. Now we come to the area element, and the area element is our dA. So area element is our dA, and this dA will be equal to our dx times dy. And so if we consider any point that is xy, you can say for any point xy, the distance from the charge element to p. So for any element xy, we can say that our r will be equal to x square plus y square and its square root. Okay. So it means within this strip, if you take any point, So this distance will be equal to over r. So this is over x and this is over y. So r will be equal to over x square plus y square. And now we come back to our this potential contribution. Okay. Now because we got our limits, therefore we can say that our potential contribution of one vertical strip, and let us call this our d phi, then this d phi will be equal to our charge density upon 4 pi epsilon naught integration, and we have this as our dy, and the distance is our r, and r is equal to over x square plus y square and its square root, and this is our dx, and the limit is from our 0 to, that is our a 1 minus x upon b. So let me write it here, it's separately. So we get our d of phi will be equal to charge density and 4 pi epsilon naught integration 0, and this comes as our a 1 minus x upon b. This comes as our dy upon x square plus y square square root times dx. Now we are simply going to integrate it, and for integration let us focus on first of all this part, and so we can say that our integration dy x square plus y square and square root, which is quite straightforward, that will be equal to natural log of our y plus square root of our x square plus y square, and we have the limits also. So the limits are from 0 to a 1 minus x upon b, and this will be giving a little bit lengthy solution, and that will be equal to the natural log x, and it will be coming as a 1 minus x upon b plus x square plus a square and 1 minus x upon b and whole square, okay, and its square root. So this is our limit. Now we substitute it back into our flux part. Therefore we get that our flux, sorry, it's not flux, potential, phi is our potential, and this comes as sigma upon 4 pi epsilon naught natural log of, so this will be x a 1 minus x upon b plus x square plus a square 1 minus x upon b whole square and its square root. Okay. Now we have little bit of more calculation is left, because we have to, one thing I forgot to write here, that is our dx. Okay. Now we have to integrate it over our x part also, that is our total potential. Okay. So we can say that total potential at P, total potential at P, and this is quite easy to understand. What we found out? We found out that the potential because of this strip at point P, let me draw it here. Okay, so we were having this right angle triangle, and we considered a strip of area dA, and the width was our dx and it was our dy. So we found out what is the potential because of this strip at point P. But we have to find out what is the potential because of this PQR, entire this surface, which is our right angle triangle. So it means we have to add, or we have to move this as per same as our, you can say, area under the curve. So this we can consider another strip, this will be our another strip. So these strips will be moving from x is equal to 0 to x is equal to b. So it means the total potential at P will be equal to, let us suppose that is our x of P. This will be equal to our integration of our d phi dx, and x is going to vary from 0 to b. So this is our important part here. Okay. So we found out, in the first step we found out that our potential because of dA, the small area at our P, which we considered as our d phi. Then we are going to divide this entire PQR in n number of strips. Okay. So we are simply going to add them, which is we are doing with the help of the integration, and our limits are going to vary from x is equal to from 0 to b. Okay. Now we substitute our d phi. So we get this, our potential at P will be equal to our sigma upon 4 pi epsilon naught, and this is our integration from our 0 to b, natural log of x, and this comes as a 1 minus x upon b plus x square plus a square x minus b upon whole square and square root and dx. Okay. And so we are going to integrate by, you can say, using the angle. That will be much more easier to solve, because we are given to us that our tangent of theta is equal to over a upon b. Okay. So from here we can say that our sine of theta will be equal to a upon a square plus b square and a square root, and our cos of theta will be equal to b upon a square plus b square. So let us assume that our x is equal to b cos alpha. Let x is equal to b cos alpha. Therefore we get our dx will be equal to minus b sin alpha and d alpha. Now we have to switch the limits. So at x equal to 0, we are going to get our alpha is equal to our pi by 2, and at x equal to b, we are going to get that alpha is equal to 0. And so only the lengthy part is left in order to find out the this solve our internal part. So I am simply going to substitute the final result. So we get our phi of P, that is a potential, will be equal to sigma b 4 pi epsilon naught integral, and this is our 0 to secant of alpha and d alpha. And our alpha is varying from our this x was 0, pi by 2 to 0. And the secant of alpha will be giving us integration of our natural log secant alpha and tangent alpha. Okay. And it is much more easier to write this in terms of our theta, okay? Because ultimately the answer is in our theta. So you can say it will be from 0 to theta. And so we get this as our, because of our this integration secant of alpha, this will be our natural log of our secant alpha plus tangent alpha. Therefore we get that as our potential at point P will be equal to sigma b upon 4 pi epsilon naught natural log of our secant theta plus tangent theta. And if we want to resolve, we can so resolve it further. Secant will be equal to 1 upon cos and tangent will be sine upon cos. Okay, but that is only part of calculation. So this is our potential at point P. So here we have to remember one important thing, that this was our shape of the surface, and here we considered a small strip with the dx and height dy, and we found out the potential because of this strip at point P, that was our d phi. Okay. And when we found our d phi, we integrated it with respect to our coordinates of our y, that is our dy. But we have to find out for this entire area, so it means we have to consider n number of strips and add them. Okay. Therefore this flux potential at P, that is our phi of P, will be now the integration of this our d phi in terms of our dx, and dx will be from 0 to b. So we have to do a double integration in this case. Okay, so we have to keep this in mind. Next question. In this case, we are given, we have two metal spheres of radii r1 and r2 quite far apart from one another compared to these radii. Given a total amount of charge q which we have to divide between them, between the spheres, how should it be divided so that to make the potential energy of the resulting charge distribution as small as possible? So we have to make sure basically the charge, our potential energy is minimum, and we have to divide this charge q as per that condition. Okay. And so we are having two spheres. So this is sphere number 1 having radius of r1, and this is sphere number 2 having a radius of our r2. Okay. And for sake of convenience, let us assume that sphere number 1 is having a charge q1 and sphere number 2 is having charge q2. Total charge on both is given as capital Q. It means q1 plus q2 will be equal to q. Okay, that is given to us. And it is also said that they are isolated conducting spheres. Okay, they are not physically connected with each other. So we are going to start, because we know that these are charged conducting sphere. So let us start with the effect of the capacitance in our charge conducting sphere. So we know that for a conducting sphere, of radius r, capacitance which is C will be equal to over 4 pi epsilon naught times r. And from here we can also write the electrostatic energy. So we can say the energy that will be associated with this conducting sphere, that is our U, will be equal to 1/2 charge square upon C. And with substitute value of C, we can write this will be equal to our 1/8 pi epsilon naught and Q upon R square. Okay, and this is for any conducting sphere R. Okay, so accordingly we can just modify our relationship. So we have two spheres, so this energy we can divide into two parts. So we can say for sphere 1, okay, so let us say this is sphere 1 and this is sphere 2. Sphere 1 and sphere 2. So you can say for sphere 1, let us suppose our energy is our U1. So this U1 will be equal to 1/8 epsilon naught. Charge is our Q1, radius is our R1. And for sphere 2, let us suppose that is our U2 and that will be equal to 1/8 pi epsilon naught. Charge is our Q2 and radius is our R2. Therefore, total energy and the total energy, let us suppose, is our U total is equal to our U1 plus U2. So we can say that our U total will be equal to, we can take this as our (1/8 pi epsilon naught) as a common. So this will be our Q1 upon R1 square plus Q2 upon R2 square. And we already know that our Q1 plus Q2 is equal to total charge, that is given as Q. So from here we can write our Q2 will be equal to our Q1 minus Q. So we simply, one second, missed it, this is square. So we get our total energy will be equal to 1/8 pi epsilon naught, and this is our Q1 square R1 square plus, we get this as Q minus Q1, sorry, it is minus and this is plus, whole square upon R2, one second, radius square. There is no radius square. Okay, square is with the charge, not with the radius. And so we want that this total energy should be minimum. So we want that our U total should be minimum. So obviously we can say our differentiation of this our U total with respect to our charge Q1, we put equal to 0. That is the basic of our this minimization. And so we can just ignore the constant part here and we derivate this internal thing. We are going to get this as our twice Q1 upon R1, and that will be equal to minus of. So from here, let me still put it here. So we get this as twice Q1 upon our R1, and this will be plus twice Q minus Q1 upon R and multiply by minus 1 is equal to 0. So once again we can just go away with this 2. So we get this as our Q1 upon R1 is equal to q minus q1 upon r2. And from here we can say that our q1 will be equal to q upon r1 plus r2, and similarly we can say that our q2 will be q times r2 r1 plus r2. And in terms of ratio, we can say that our q1 ratio q2 will be equal to our ratio r1 to r2. So when our charges on individual spheres is proportional to their radius, we are going to get our energy is equal to minimum energy. And next question is somewhat similar to this one, but it is being framed in a quite different way. Okay, we'll see to that. And there are some extra questions to that also. So we are given that suppose we have a metallic solid sphere of radius r. It carries a charge q. What is the potential energy of this sphere? Okay, so this is the basic one. The part B. Now consider two metallic sphere of radius r1 and r2 far apart, sufficiently far away they don't electrically interact. We have a total amount of charge q that needs to be distributed on these spheres. Suppose F times q goes into one sphere and 1 minus F times q goes on to other. For what fraction of F is the total potential energy minimized? Okay, but same question but framed in a little bit typical way. Okay, answer will be, you can clearly see that the ratio will be coming as same. And part C, what is the potential difference between the sphere in the electrostatic ground state? Part D, what is the electric field along the axis joining the center of the spheres? Part E, if the first sphere carries all the charge q, is then connected to the second far away sphere by a metallic wire, will the charge redistributed? If yes, then how? But we are mainly interested in this part B. Rest of the things are quite simple. Okay. So we start with our part A. Part A is going to give us a basic formula which we are going to use for our this energy part. Okay. We can just derive this energy of a single metallic sphere. Energy of single metallic sphere. Okay. And we are given that a metallic sphere, its radius is given to us as r and charge is our q. And so let us generalize it, and we are suppose that the sphere is carrying a charge of small q. Let us assume that sphere is having a initial charge of small q. Therefore, we can say its potential and potential due to this small charge q, initial charge q, will be equal to 1 upon 4 pi epsilon naught q upon r. Okay. And we are now bringing a small charge from infinity to this sphere. Okay, and let us suppose that small charge is our dq. Okay, and in this case we have assumed that it is having initial charge q. Okay, capital Q will come later on because that is only part of our final answer. If we can say to bring bring additional dq charge from infinity the required work, or we can say energy. You can see the required work and let us call that work as part of our energy, that is our du. Therefore we can say that our du will be equal to already potential because of charge q times dq. So this comes as 1 upon 4 pi epsilon naught q upon r times dq. Now we can say our total energy we started from our q is equal to 0 to final q is equal to capital Q. Therefore we can say that our u total energy will be our integration from 0 to q, and this is our du. Okay. And we can simply substitute it. Is 0 to capital Q 1 upon 4 pi epsilon naught, and this comes as q upon r, and this is our dq, and this is quite simple. We get this as q square upon 8 pi epsilon naught times r. So we can find out the total energy associated with the conducting sphere. In the previous question we solved the same but using the capacitance, and this is a more traditional approach which we study in the books also. Okay. So this was our part A. Now we come to part B, and part B, it states that now we are having two conducting spheres. So this is our first conducting sphere of radius r1. So this is sphere 1, and far away we are having another sphere of radius of r2. So this is our sphere 2, and once again here charge is our q1, here charge is our q2, but total charge is given to us as our q. And it is also mentioned that q1 is our fraction of our this q, and this q2 is also a fraction of our q, but in terms of 1 minus f times q, and if you add them, their summation will be equal to our q. So this is our charge distribution. Therefore we can say total energy will be equal to, let us suppose this is our energy of u1, this is energy of u2. So total energy will be equal to the summation of our individual energies. So we can say our total energy that is our ut will be equal to u1 plus u2, and that we already know, that is 1 upon 8 pi epsilon naught we can take as common. This is 1 upon 8 pi epsilon naught, and we get this as our q square. Q is here fq whole square upon r1 plus 1 minus f q, and this comes as whole square upon r2. And so we can take q also outside. So we get this our total energy will be equal to our q square 8 pi epsilon naught. We have this as r1 f square plus r2 1 minus f whole square, and we want it to be a minimum. Okay. So we can say once again u2 total energy, we want this as minimum. So we can say its differentiation with respect to charge q, we are going to put equal to 0. And if you derivate it, we can just ignore this part. So we get this as our 2f upon r1, and this will be a plus twice 1 minus f and minus 1 upon r2 is equal to 0. So once again 2 and 2 we can just ignore, and from here we get that f upon r1 is equal to 1 minus f upon r2, and we can solve it for f. We get this as our r2f is equal to r1 1 minus f. Therefore we get that the fractional part f will be equal to r1 plus r2. And we can also find out our minimum energy, that is our U total minimum will be equal to, this comes as our Q square. We simply substitute value of this F, and this comes as 8 pi epsilon naught. So in the first part we have 1 upon R1, and this is our R1 plus R2 whole square plus 1 upon R2, and this is 1 minus F, so it will be our R2 upon R1 plus R2 whole square. So we get the minimum energy will be equal to our Q square upon 8 pi epsilon naught, and this will be equal to our one upon R1 plus R2. So this is the minimum energy that will be associated. And once again we can find out the respective charges also. Like in the first case, our Q1 will be coming equal to our Q, that is our R1 plus R2, and our Q2 will be equal to Q R2 R1 plus R2. Similarly, in this case, our ratio will be equal to our R1 is to R2. And if required, we can find out this ratio in terms of F also. Okay, that is only a little bit lengthy part here. Okay. Next, we come to our part D, that is electric field. Okay, so in this case, in part B, we clearly see that the ratio of their charges is still our R1 and R2. The question was asked in a little bit typical way. Okay, they simply extended the statement by introducing a fractional part, that is our F. Okay, that was only the difference. Rest was our simple. So next is our part D. And in part D, we have to find out the electric field along the line joining them. So this is our sphere 1 and this is sphere 2. These are the centers, and suppose this is the line joining them. And this center we are going to take it x equal to 0, and this we are going to take it x is equal to d. So therefore the distance between the center is our d. Okay. And we are going to take any point randomly somewhere here which is at a distance x. So from the other end it will be at a distance of over x minus d. Okay. So this is our sphere 1 and this is our sphere 2. Therefore we can say that our sphere 1, we assume that its center is x is equal to 0, and for sphere 2 we have assumed that its center is at x equal to d. Okay. And this distance d is very much greater than their individual radii. Okay. And so electric field between this point, let us suppose this is our point P. So we can say that our electric field at point P will be nothing but the algebraic sum of both the electric fields. Okay. And the you can say we have two charges. So the electric field will be from our first sphere will be pointing towards the right side, and because of the second sphere it will be pointing towards left. So both will be in opposite direction, but the magnitude will be different because the radii is different and the distance is also different. Therefore we can say that net electric field at point P will be the difference between the two, 1 upon epsilon naught, and charge on first one was our q1 and the distance is our x square minus this is our q2 and charge distance is our d minus x upon whole square. So this is the value of electric field. Okay, there is no need to solve it because the variables are not known to us. And in part E, it states that now both the spheres are connected through a metallic wire. Okay, so we are having this sphere 1 and sphere 2, and in this case it was given that entire charge is only on sphere 1 at start. Okay, and the charge on initial charge on sphere 2 is equal to 0. Then they are connected with the metallic wire. So obviously we know that charge transfer is bound to happen, and this is going to until the potential becomes same. Okay, so let's assume that this is having a V1 potential and this is our V2 potential. So charge is going to transfer is going to take place until V1 is equal to V2. So we can say initial state we are given that our sphere 1 is having a charge which is our q, and let us suppose the potential is our V1, so that will be q upon 4 pi epsilon naught, and we have this as r1 square. And then we have our sphere 2 charge, initial charge is equal to 0 and initial potential, that is V2, is equal to 0. Now we come to our final state. Final state means connection by the wire. Connection by wire. Okay. So the final condition is going to give us that our V1 should be equal to V2. And we already know that so after connection, let us assume that in the final state our sphere 1 is having a charge of q1 prime and sphere 2 is having a charge of q2 prime, and so V1 is equal to V2, or let me say that this V1 prime is equal to V2 prime. Okay, because initially we have assumed this as V1 and V2. Okay, so we can now substitute it. So our V1 prime will be equal to our q1 upon 4 pi epsilon naught, and the potential doesn't have square. So this is 4 pi epsilon naught r1 will be equal to q2 prime 4 pi epsilon naught upon r2. So once again from here we get that q1 prime ratio q2 prime will be equal to our r1 ratio r2. Okay, but the total charge will be same. Okay, there is no loss of charge. So our q1 prime plus q2 prime will be still equal to q. Okay? There will be no loss of charge because loss of charge conservation. So after connection and before connection, the charges will be same. So Q1 prime and Q2 prime is the charges, total charge after connection, and Q is the total charge before connection because the second sphere was having a charge of 0. And we can find out that our, as we did in the first case, that our Q1 prime will be equal to Q upon R1, R1 plus R2, and our Q2 prime will be equal to Q R2 R1 plus R2. Okay. So these were the few variations of our given question. Okay. So we have to keep in mind that the same question can be asked in a different way, especially the last two questions. If you compare, the statements are entirely different. Okay. But the ultimate, the answer will be coming same. Okay. So always focus on the process of doing the question. Okay. If the process is correct, you are bound to get the correct answer. So this completes all the questions for today. Thank you.